So today we're going to be talking about molecular geometry and something called VSEPR theory. So VSEPR is an acronym, and I realize that the E is after the S. When you look at that, I get it, but we usually just call it VSEPR theory. So what VSEPR theory stands for is valence, shell, electron, pair, repulsion. So it's valence shell electron pair repulsion theory. It's a bit of a mouthful to say all of that, so we shorten it to VSEPR. I mean, if you want to go by the letters and the order they are, you could call it VSEPR, but that just sounds weird. So VSEPR is what we usually refer to it as. VSEPR theory, basically molecular geometry, the shapes that molecules have when they are bonded together, and you have the central atom and the outside atoms. They're going to form shapes. Now, the reason it's called valence shell electron pair repulsion is because it all has to do with the electrons, as much of the bonding in chemistry does. So electrons are all negative, and negative charges don't like each other. They push away, they repel. Negative charge here, they're going to push each other away. So the electrons want to be as far away from each other as they possibly can. So when elements form covalent bonds, you've got an atom that is sharing electrons with this one, they're sharing, but then there's all the other electrons on this atom also, not just the ones that are being shared. There's the other electrons there, and then it's sharing with this atom, and it's got all of its electrons. Well, the electrons in this atom, are going to want to be as far away from each other as they possibly can, so they repel each other. That's the repulsion part of it. So you've got the valence shell, the outer electrons of the outside atoms. The valence shell electrons are repelling each other. So that's why it's called valence shell electron pair repulsion. So they're going to push apart, and it gives a geometric shape depending on how the molecule is put together, how many atoms there are attached to the central atom, and whether or not there are lone pairs of electrons on the central atom that are not bonded, just regular electrons sitting there that are not bonded. Those will push out and change the shape of the molecule as well. So these shapes can also help you determine if a molecule is polar or nonpolar. We talked about that a little bit in a previous video where we discussed polar and nonpolar bonds versus polar and nonpolar molecules. But this VSEPR theory is going to show us exactly how to tell. So basically, if a molecule is symmetrical, and I don't mean like just split down the middle symmetrical, but symmetrical this way and this way and this way and this way, molecules are three-dimensional things. So if it's three-dimensionally symmetrical, it is a nonpolar molecule. If it is asymmetrical or non-symmetrical, you're going to have a polar molecule, because if it's not symmetrical, that means you're going to have a slightly positive side and a slightly negative side, because all of those individual bonds are nonpolar. If you have nonpolarness to the molecule, it's going to be because you have an asymmetry to the molecule. It's going to mean that you're going to have a slightly negative side and a slightly positive side. All right, so most covalent compounds are going to have a central atom and outside atoms. We learned about that when we talked about the Lewis diagrams for covalent compounds. So VSEPR shape is determined by the arrangement of those outside atoms. And there are lots of different VSEPR shapes, but there's only 4 or 5 that we're actually going to talk about right now in this class. And if you get into higher level classes, you'll learn about the hybridization of the valence shells, and we're not really going to get into all of the hybridizations because it's kind of complicated and really not necessary for a basic chemistry class. So the first shape we're going to talk about is a linear molecule, and linear is exactly what it sounds like, a line. All right, that means the molecule forms a straight line. That means all elements in the compound, all atoms in the compound form a straight line. So if you only have 2 atoms like carbon monoxide, CO, then you're going to have a linear molecule. If there's only 2 atoms, then you have a linear molecule because 2 points form a line, basic geometry. Now, if you have more than 2, so say you have 3 elements or 3 atoms in your compound, those atoms have to form a straight line for it to be linear. So here would be an example. This is a picture of I'm not exactly sure what you would say this picture is. It's very similar to carbon dioxide, so we'll just call it carbon dioxide here. So you've got carbon in the middle and two oxygens on either side. It is a linear molecule because they form a straight line. It is also nonpolar because when you cut it down this way, you draw a line through it this way, the left and the right are exactly the same. If you go horizontally, the top and the bottom are exactly the same. No matter how you cut it, each side is equal to the other side. It is a non-polar shape. Okay. Now you can have a polar linear molecule if you only have two. So like carbon monoxide is a polar molecule because it's only two and it's a polar bond. But that means you just have to kind of look at, if you only have two atoms in a molecule, it is going to be linear. And if it is not a diatomic molecule like O2 or H2, if it's not diatomic, but there are only two atoms, then it is going to be polar because it's going to be a polar bond regardless. So if you only have two atoms, it's going to be linear and it will be polar. So polar or linear shapes are sometimes polar, sometimes nonpolar. It depends on whether or not you have two or three atoms. A three-atomed linear molecule is pretty much always going to be nonpolar. A two-atomed linear molecule is going to be polar unless it's a diatomic molecule, meaning two atoms of the same element. Hopefully that is not too incredibly confusing. So the next thing is the bent molecule. A bent molecule is exactly what it sounds like. It's bent. All right. It forms when the central atom has two unshared electron pairs that push the atoms away, push the other outside atoms away. So if you take that linear one that we just had, where you had the central atom and the two outside atoms, if you add unshared electrons to the middle, those unshared electrons are going to repel the electrons of the outside atoms and push them down, giving you a bent shape. And that's what happens here. So this would be a diagram of what water looks like, where you have oxygen here in the middle, and then you have your two hydrogens. Well, oxygen is also going to have two unpaired or unshared pairs of electrons. Those two unshared pairs of electrons are going to push these hydrogen atoms down, giving it a bent shape. So water is a bent molecule, and it is polar. Because it is bent, you have the negative electrons up here plus the polar nature of the bonds. So this is a negative side to the atom, and then the hydrogen sides would be the positive side to the molecule. And so you have a line that you can draw right here separating the negative from the positive. So it is a polar shape. Bent molecules are pretty much always going to be polar. Now we have the next shape is called trigonal planar. Now, trigonal, think about that for a second. Triangle. So it's triangle. Planar means plane, flat. All right. So there's some geometry words here. We got triangular or trigonal, and then it's flat like a tabletop or a plane. So trigonal planar is going to be a flat triangle, and it forms when there are three outside atoms and no unshared electron pairs. All right, so we have something like this, where you've got your central atom and then three atoms on the outside, and they're all in the same plane. So if I were to take this molecule and set it on the table, it would lay flat, and all four of those atoms would be touching. So you've got four atoms in there, but there's one central atom and three outside atoms. That's trigonal planar. And it is nonpolar, because again, we can't separate the positive from the negative. So let's just say that these were hydrogens on the outside. They would be slightly positive because of the polar bonds. Hydrogen's pretty much always going to be the least electronegative that you're joining with in a covalent compound. So you're going to have the covalent bonds themselves are going to be polar, and you're going to have that hydrogen is going to be slightly positive, so that central atom is going to be slightly negative, but we can't separate the positive of the three hydrogens from the central atom there. So it is a nonpolar molecule, even though the bonds themselves are polar. Now we have trigonal pyramidal. So again, triangular, trigonal, it's going to be a triangle, but it's a pyramid. Instead of being flat, it's going to be poking up like a pyramid. So this is a pyramid with a triangular base, a triangular pyramid. So trigonal pyramidal. That forms when there are 3 outside atoms and 1 unshared electron pair on the central atom. Okay, so that's going to cause something that looks like this. So you're going to have that central atom has some unshared electron pair up here, and this unshared electron pair is going to be pushing those down, just like it did with the bent. So it takes that planar triangle and it pushes those down, so it now has a part that's sticking up and the triangle that's down, so it's a triangle pyramid, okay? And since, of course, you've got a negative side up here where those extra electrons are, and the positive side down at the bottom because of the polar nature of the bonds, this is going to be a polar molecule, because we can, just like we did with the bent, we can draw a line that separates the positive above from the negative below, or sorry, negative above, positive below in this case. So we can draw a line and separating them, so it is a polar molecule. Now we have tetrahedral. That's a fun word to say. Tetrahedral. Now, tetra means 4. Okay, so this forms when there are 4 outside atoms and no unshared electron pairs. So you're going to have a central atom and 4 things attached to it, and those 4 things are going to spread out as evenly as possible. Now, we often draw them to look kind of like a plus sign because, well, that's the easiest way to draw it in a 2-dimensional piece of paper. However, electrons and molecules don't exist in 2-dimensional space. They exist in 3-dimensional space. So to get as far apart of each other, they actually don't make a plus sign. They make a tetrahedron, or that's why it's called tetrahedral. If you've ever played the game Jacks with the little pointy things that you roll on the ground, that's what a tetrahedron looks like. So this is a tetrahedral molecule. So you'll notice the central atom here, and then those 4 outside parts, it's basically like a trigonal pyramid, except instead of having nothing on the top, you have something sticking up off the top. So all 4 of those outside atoms are as far away from each other as they possibly can be in 3-dimensional space. And that's what tetrahedral looks like. Lots of compounds are tetrahedral, and because there are 4 on all the outside, it is a symmetrical molecule, and therefore it is non-polar. The last one we're going to talk about here is trigonal bipyramidal. So again, trigonal, so you're going to have 3 things around the outside. Bipyramidal means 2, bi, like a bicycle, 2 pyramids. So it's basically taking the trigonal pyramidal and another pyramid, and they're stacked on top of each other. Right? This forms when there are 5 outside atoms and no unshared electron pairs. This happens only with certain central atoms can do this, because only certain central atoms have the ability to what we call expand their octet and have more than 4 bonds. We'll get into that a little bit later. But this is what a trigonal bipyramidal looks like. You've got the 3 around the middle that are all in the same plane as the central atom, and then you're going to have 1 above and 1 below, making a pyramid at the top and a pyramid at the bottom, and that's where the bipyramidal comes from. So you've got linear, bent, trigonal planar, trigonal bipyramidal, tetrahedral, trigonal pyramidal. Those are the shapes that we're talking about. Oh, and by the way, trigonal bipyramidal is a non-polar molecule because it is symmetrical. So these are the shapes that we are going to learn about, that we're going to talk about in this class. There are plenty of others, and there's a lot more to VSEPR theory than just this. But as far as this basic class goes, this is the extent of VSEPR theory that we need to talk about. So in the next unit we're going to get into is going to be talking about how we name and write chemical compounds and write the formulas for chemical things. It's the nomenclature, how we name it. So look forward to that. Thanks for watching, and have a day.